Here we go. So hello everyone. My name is Jacopo and I'm the lead machine learning engineer at LightOn. And today we are with Charlotte Frenkel and Martin Lefebvre. And they're gonna give a presentation on learning without feedback, fixed random learning signals, allow for feed-forward training of deep neural networks. Charlotte is a postdoctoral researcher at the Institute of Neuroinformatics and ATH Zürich in Switzerland. And Martin is a teaching assistant and PhD student at the Institute of Information and Communication Technologies, the Université catholique de Louvain in Belgium. So yeah, Charlotte, Martin, the show is yours. I think you can start your presentation.
Thank you all for attending this presentation, and thanks again to LightOn for inviting us and giving us this opportunity. So I'm Charlotte, and I'm here with Martin to present you a work entitled Learning Without Feedback. And so I'll start first with a little bit of context. So basically, Martin and I are integrated circuit designers, and we are focusing on edge computing. So edge computing is basically near sensor computing. So it's decentralized, low footprint, smart sensors. So maybe you can think of the Internet of Things, for example. And one key feature of such devices is progressively to embed learning directly into the sensor, both to make it configurable and to make it user customizable. So it has several advantages. It can increase the lifetime of the device, and it also avoids resorting to the cloud. So that means that we can reduce latency in case we need to tune the algorithm inside. We need to reduce power consumption on chip because we avoid the cost of communication. And embedding learning or customization on chip can also be a strict requirement just for privacy reasons, for example. So the issue here is that, for example, we could think that back-prop is a standard algorithm to do so, but definitely for small chips and decentralized low-footprint devices, back-prop is certainly not the good choice, due to two key reasons that really preclude the hardware efficiency of back-prop. And interestingly, these two key issues are also the same ones that make back-prop biologically implausible. So you can see on this slide a short summary of back-prop, so BP for short here. And these two issues are the following ones. So it's first the weight transport, which means that the forward and the backward weight need to be transposed of each other. And so from hardware efficiency point of view, that requires specific memory accesses and a lot of memory access patterns that are certainly not cheap because it requires specific architectures. And even from a biological plausibility point of view, it's not, I mean, synapses in the brain are unidirectional, so that's not plausible. The second issue is update lockings. For example, if you look at this layer here, you cannot update it before you get out the full forward pass followed by a full backward pass. So that means that you need to really interleave forward and backward passes. That's not biologically possible because all synapses operate in parallel in continuous time. And from a hardware efficiency point of view, that needs to buffer the activations instead of all the layers before you're able to carry out the updates. So that implies a lot of buffering in memory overhead. So now let's look at the state of the art to release these constraints. And there's the feedback alignment algorithm that solves the weight transport problem. So it, in the backward path, it replaces the weight here to you not need to transpose the weights anymore. You replace it with fixed random matrices. So that's also weight transport problem. You don't need to transpose anymore. But update locking is still there. You still need to do this forward followed by backward pass. Next, you've got the direct alignment, and instead you directly project the error through fixed random matrices to the hidden layers. And so the conclusion is the same. It solves the weight transport problem, not the update locking. Even though the latency to update in the backward path is shortened compared to feedback alignment. And then the key idea that we have and that we'll investigate is what if we replace the error here with the sign of the error? And actually we can see, and that's what we'll describe in this presentation, is that the sign of the error is already contained in the target vector that is basically just a one-hot encoding of the classification label. So for classification problems, we had that the sign of the error can be known in advance. And that's what we'll do in this presentation. And if the sign of the error is known in advance, you see that you don't need to wait for full forward pass to get this information. And that it means that you can release update locking. So that's the grounds for the algorithm that we propose, the direct random target projection, or the RTP for short, where we directly project the targets, the classification targets, to the hidden layers through fixed random connectivity matrices. And that allows to release both the weight transport and the update locking problems. So what I would like to insist on is that along all of these algorithms, you have that the computational and memory costs are reduced for hardware implementation, up to the point that you end up here with a purely feed-forward and local training algorithm. So that closes the loop with our initial target of edge computing, low-cost processing. We aim at an algorithm that is the cheapest possible, but it's still able to do the job for small processing tasks. So here it was the global overview, and now I'll take a step back. And here are 4 points of this presentation.
Charlotte?
First, yes?
Charlotte, just 1 second. There are some glitches in your voice. Maybe if you can try to cut the video, it improves.
Sure.
I don't know.
Is there anything I need to repeat before?
No, it was understandable to me, at least. It's just that like it's a bit confusing sometimes.
Okay, I'll also try to speak a bit slower then.
Okay,
in
thanks.
case there are new cuts. Okay, so the first point, and do not hesitate in case you've missed a whole sentence to interrupt me, and I'll just go over it again. So the first point that we'll tackle is to verify that taking only the sign of the error in the sign-based version of direct feedback alignment, or SDFA for short, is still able to provide learning in multi-layer networks, and we'll check that for synthetic regression and classification tasks. Then we'll highlight the differences between sign-based DFA and the RTP, and show and highlight how the RTP is able to use update locking for classification tasks. Then we'll have a look at the benchmarking results for the RTP on MNIST and C410 before concluding the presentation. So for the first point, so here it's again the global overview. We'll just focus on SDFA so far. And what we'll do here is to focus on demonstrating this claim that the weight updates based only on the error sign provide learning to multi-layer networks. And here I give the floor to Martin to show basically the results on synthetic classification and regression tasks.
So basically, to try to answer the claim that the error sign is able to provide learning to train multi-layer networks, we have considered 2 different types of problems. The first class of problems was a regression task. So could you switch? Yeah. Okay. So on this regression task, we try to approximate 10 nonlinear functions, more specifically 10 cosine functions, whose formula are given here on the slide. So the ith cosine function, which is denoted here as yi star, is given by the cosine of x bar, the mean of x, plus some phase difference phi I, which is dependent on the output neuron of the network. We'll also notice that the entries of the input vector x are drawn from a normal distribution whose mean is itself drawn from a uniform distribution between minus pi and pi, and whose variance is equal to 1. Regarding the network, we have used 10H units in the hidden and output layers, and as this is a regression task, we have used a mean squared error loss at the output of the network. So now regarding the loss, we see on both the training set and the test set that the performance that we get at the end is dominated by direct feedback alignment, or DFA, followed closely by back-propagation and FA. And then we find the method that we are using here, which is sign-based DFA. And then far away, we find what we call shallow learning. So shallow learning basically consists in only training the output layer of the network using backpropagation, but keeping the hidden layers fixed. So at the same level, with the same weights as the weights that were given by the initialization of the network. So this is the first conclusion that we can see from the graphs. The second conclusion that we can draw from this graph is that there is, of course, an accuracy loss when we use sign-based DFA, which was to be expected. And this is due to the fact that we are not using the error magnitude information. So this has two consequences on the training of multilayer networks. The first one is that there is no effective reduction of the learning rate. And this comes from the fact that as it is not dependent on the magnitude of the error, the step size that we are making during each update remains the same throughout training. So this is the first consequence. And the second consequence is that usually there is an error magnitude which is class dependent. And here we completely trash this information and only rely on the sign. So let's now have a look at the angle. The angle represents the alignment between the modulatory signals which are prescribed by training methods, here FA, DFA, and SDFA, and the modulatory signals which are usually prescribed by back-propagation. First, we see that during the first 100 epochs of training, feedback alignment has a strong advantage over DFA and SDFA, even though it still has an advantage throughout the rest of the training. Then we see that surprisingly, SDFA alignment is on par or even better on the second hidden layer than the angle provided by DFA. And then finally, we see that there is a slight increase of the alignment angle, so a slight decrease of the alignment itself when we move away from the output of the network, meaning that the angle in the first hidden layer is larger than the angle in the second hidden layer. Okay, so now let's move to the second class of problem that we have considered to tackle this claim. We are now moving to classification problems. And so our goal here is to classify 256 dimensional vectors into 10 classes. And the dataset that we are using is a synthetic dataset, which has been generated using the make classification function, which is embedded in the Python sklearn library. So here the key differences in the network with respect to what we had with regression tasks is that we use wider hidden layers with 500 units compared to 100 for the regression task. And at the output of the network, we use sigmoid output units and a binary cross entropy loss. So what are the results in terms of accuracy? First, on the training set, we see that again, DFA performs better than our training algorithm, followed by backpropagation and feedback alignment, and then by SDFA at 1.5% of training error. And then far behind, we find a shallow learning, which is at nearly 9% of training error, also on the training set. This is quite a different picture that we see on the test set. So on the test set, you see that backpropagation and feedback alignment perform on par with each other, followed by direct feedback alignment, roughly at 3.5%, and then by SDFA at 4.1%. So when moving from DFA to SDFA, there is 0.6% accuracy loss. And then far away at nearly 10%, we find shallow learning. So this is important because this shows that SDFA is able to train the hidden layers or to provide some significant training to those hidden layers compared to a training where we would only train the output layer using shallow learning. Okay, so then if we have a look at the angle, the alignment angle, we see basically the same thing as for the regression task. Feedback alignment is better than DFA and SDFA. And also the angle degrades as we move away from the output of a network. So what we have shown here is that the error sign is able to provide learning to multi-layer networks. And now what we are going to do is to do the link between this sign-based direct feedback alignment method and the method that we are proposing, which is direct random target projection, or in short, DRTP. So first, we have to notice one interesting thing. And this thing is that for classification problems, the error sign is known in advance, which means that if the error sign is known in advance, we no longer need a feedback pathway to provide updates to our network. So how come that we have this property? So first, the error vector, it is defined as the difference between the target vector y star and the output of the network that we denote yk here. If we look closely at the different entries of this vector, we see that for the entry corresponding to the correct class, so the entry corresponding to index C equals to C star, where C star is the label, we have an entry which is 1 minus YKC. And for all the other classes, so the incorrect classes, we have minus YKC. But we know that in the case of classification problems, the output units that we are using are either softmax in the case of multi-class single label problems or sigmoid in the case of multi-label problems. So it means that the output of those units is comprised between 0 and 1. And this has an impact on the sign of the entries in the error vector. And we see that for the correct class, the entry is positive, while for all the other classes, the entry is negative. And for a given example in the training set or the test set, this is a property that is not going to change throughout training. This is not going to change. And basically, you know that this information is the same as the information which is contained in the target vector y star. Why? Because in the target vector y star, for the correct class, you have an entry which is 1. And for all the other classes, you have entries which are 0. This is the same information as the sign of the error, where we have a different entry for the incorrect class and for the correct class, sorry, and the incorrect classes. And this is exactly the idea that we use to develop direct random target projection, or DRTP, which is able to deliver useful modulatory signals to our networks. So here you see on the right-hand side of a slide the illustration of SDFA versus DRTP. And you see one thing that is very interesting is that DRTP is able to release the update locking problem. And so it is a purely feed-forward local training that we are applying to the network. And DRTP can be considered as a simplified version of SDFA due to the fact that it relies on the same information as the information contained in the sign of the error. But still, there are two major differences between those algorithms. First, it is that DRTP is computationally cheaper than SDFA. In DRTP, we are performing a label-dependent selection of a layerwise random vector. Basically, we are getting a column from our random connectivity matrix. While in SDFA, we have to perform a full matrix product between the error vector and the random fixed random matrix, which is our feedback connectivity matrix. Then the second major difference is that DRTP systematically outperforms SDFA over the MNIST and CIFAR10 datasets. And this is something that we have proved empirically in our paper. So what is the intuition behind this result? Well, in the DRTP algorithm, only the correct class has an impact on the learning, while in SDFA, all the other classes, the incorrect classes, also have an impact because they have a minus one value due to the sign of the error. And so those incorrect entries, they will outweigh the correct class, and so this will lead to poor training performances. So then the second argument, which is supporting the fact that DRTP provides useful modulatory signals, is the fact that we have proved in our paper that the directions of DRTP and BP modulatory signals are aligned, are within 90 degrees of each other, which can also be translated into the fact that there is a soft alignment between the forward and feedback weights. But this is in a very specific case, and we will have the occasion to come back later to that if you have some question about it. So now I will leave the floor to Charlotte, which will speak about the MNIST and CIFAR10 datasets.
So if we are to come back to our, again, base context of edge computing, we selected the MNIST and CIFAR10 datasets for the simple reason that they represent meaningful benchmarks for small decentralized smart sensors.
Charlotte, sorry to interrupt you again. Yes. The volume is a bit low. Can you speak louder or closer to the microphone, maybe?
I'll try to. Is it better like this?
Can you talk?
Is it better like this?
Yeah, it's a bit better, but still not enough, I think. I mean, it's understandable, but very
seems in my settings that the microphone is at the maximum. I haven't changed anything.
What you're saying is very choppy.
Maybe I disconnect and reconnect then, because I don't know, nothing has changed in my settings.
Now it seems better for some reason.
Okay, just tell me if it goes worse again. So we have chosen the MNIST and CIFAR10 datasets because they represent meaningful benchmarks for smart sensors. And this is also the reason why we haven't chosen bigger datasets like ImageNet, because they do not make sense for such a context. So for MNIST first, here's the array of results. And I go directly to the key messages. On the fully connected networks, we have that performance degrades as the backprop constraints are relaxed, so it degrades progressively. And the RTP is still competitive. So here the key claim that we want to make, so of course, compared to the relaxed requirements of the RTP, we expect a penalty, and we would like to show that this penalty is acceptable for edge computing. So that's for fully connected networks, the RTP is still competitive. If we look into convolutional neural networks, we have that if the convolutional layers are fixed at random weight and aren't trained, all training algorithms lie close to each other on MNIST. Only the fully connected layers are trained. And that means two things. The RTP is, again, also competitive, but that also means that MNIST is a simple benchmark that where selecting random convolutional layers is quite enough. But if we train these convolutional layers, we have that backprop provides an improvement, but it's not really the case for the feedback alignment-based algorithms. So feedback alignment improves slightly, but DFA even degrades it while it almost doesn't move for the RTP. And the reason behind it is it's something that has been documented in the literature as the bottleneck effect. So for performance to improve with feedback alignment-based algorithms, we need redundancy in the parameters. And this redundancy in parameters actually is not offered in convolutional layers, only for fully connected layers. But so that's basically it. And for CIFAR10 results, basically all the conclusions that have been drawn for MNIST also hold in this case too. So now is already the time to conclude with some key messages and the perspectives. So for the take-home messages, we have 4 take-home messages for you. The first one is that the error sign is sufficient to provide learning to multi-layer networks. We have shown that with the sign-based version of direct feedback alignment. The second one is that the error sign is known in advance for classification problems, thanks to the target vector that represents a one-hot encoding of the classification labels. And this thing allows solving the update locking problem and has to be combined with the first take-home message. So from that, we propose a direct random target prediction algorithm, and we show both experimentally and theoretically, and for the theoretical demonstration, as Martin said, is in the paper, it leads to a soft alignment between the forward and backward weights, because the modulatory signals prescribed by the RTP are within 90 degrees of those prescribed by backprop. And finally, that the RTP is demonstrated on the MNIST and CIFAR10 dataset, which makes sense for edge computing. And so for the outlook, I would like to point to things. So on the neuroscience side, we've got that very interesting recent findings that have identified in cortical areas the existence of output-independent target signals, which are located in the dendritic constructive pathways of intermediate layer neurons. So that's really interesting because it comes in line with the RTP. And here, I'm not saying that the RTP is the algorithm that operates in the brain, but maybe comes in line with some of the mechanism that the brain uses. And the RTP also comes in line with the formulation of 3-factor synaptic plasticity rules, which is a common way to frame synaptic plasticity. So it does make sense from a neuroscience point of view. And also, we have, we made this claim of edge computing during all the presentation, and therefore we demonstrated it in a circuit implementation. So we show that implementing the RTP into silicon only costs about an overhead of 15% in silicon area in power, which is a record to implement learning on chip. And therefore you can check this reference for further information. that comes to an end, therefore, and I would just like to point out a few further resources. So a link to the preprint of the DRTP algorithm, a link to the open source PyTorch code that implements DRTP, but also direct feedback alignment and feedback alignment. And finally, a link to the preprint of the silicon implementation of DRTP. It's a paper that has been accepted at ISCAS. It's not yet available, but it should be in the upcoming days together with the video of the associated talk. So thank you for your attention, and both Martin and I are now available to answer any question you might have.
Thank you, Charlotte, and thank you, Martin. Yeah, claps on Zoom are weird, but I don't know if you people know there are like reactions and you can use.
We see them.
Yeah. Yeah, so now I just want to say one thing, that I really want to thank you also, Victoire, who did most of the organization for the meetup and couldn't join us today. And I'm just taking her work and taking the credit. So no, the credit goes to Victoire. And now it's time for the questions. So as I said at the beginning, but not all of the people that joined at that point, you can either write them on the chat and I will ask them, or raise your hand or directly unmute yourself to ask questions. So there are any questions? I know Ruben has one.
Hi, I have a question. So from your first plot, I may have seen that GFA performed better than BP. Isn't it a very good result or something? Yeah, here. Maybe before, I don't know, but yes, GFA performed better than BP, right? On the test error.
Maybe I'll take this one, and Martin we will complete. So one thing that we have to point out here is that these experiments have been done with a constant learning rate, which is the same for all methods here. So it's just to show basically the convergence of all methods. And definitely, if we were to obtain the best result for every single method, we would need to run a learning rate selection for every different algorithm, which is what we did for MS and CFAR10. But here it allows showing basically the convergence properties. And also it allows pointing out an interesting effect is that feedback alignment and BP tend to suffer a little bit more from the vanishing gradients than direct feedback alignment, because it has this direct link to the hidden layer, direct projection to the hidden layers. So that's, these are the two elements that explain this, because these results were extracted mainly for illustration purposes, but definitely if we want to extract the best performance, we need to go through a hyperparameter selection for each algorithm.
Okay, thank you.
Okay, thanks. There is a question from Yaman Umuroglu. I think I'm pronouncing it correctly. What's the impacts of the choice of random metrics on the feedback path on the final accuracy and performance in training?
Maybe I can take this one and Charlotte will complement if need be. So here we did not experiment that much with the random matrices, but one thing is certain: in the method that we propose in DRTP, the norm of the values inside this matrix has a direct impact on the learning rate, because we just select one column of that matrix, and this column will be used as a surrogate for the gradients. So if you have larger values, you will have like larger gradients. So this has an impact on the convergence. But then on the type of matrix here, we just drawn weights from uniform distribution. It's a Hay distribution basically. But we did not explore other types of random matrices. And maybe one interesting comment regarding the proof that we have made. Actually, there is at no point do we use any property of this matrix. This is just a matrix. This could be anything. So I guess that there is room for some experimentation on that side.
Thank you for the answer. Are there any other questions?
Yes, I do have one.
Yeah, go ahead.
First, thank you for this very nice presentation and for this very interesting work. I think the idea that using only the sign can actually lead to forward unlocking it's a very fun and exciting idea. I have just a general question, which is on slide 6 on the graph on slide 6, which which are the simple experiments. So you say that you lose a lot of performance because the class dependent, because there is no reduction of the effective learning rate as training progresses. Is that not, have you experimented with recovering that, that effective reduction, for instance, by using like a schedule on the learning rate or something like that?
Charlotte, you want to answer, or maybe I start? What do you prefer?
Yeah, actually, we haven't experimented too much with this one. In the paper, we point out that for this no reduction of effective learning rate as training progresses, indeed, for the first aspect, a learning rate scheduler can help. And we have made some preliminary experiments for this. I don't remember whether it was for regression or classification, but we indeed saw, like for SDFA, at each step of the scheduler, this error tended to go down. So this is just something that we point out in the paper, but we haven't experimented much more with it. But in any case, even if you find an optimum scheduler with an optimum stepping of the learning rate, this doesn't help for the second factor, that the class-dependent error magnitude is lost. So it's just for the global magnitude of the learning rate, but not, for example, if one class suffers from a high error rate and compared to the others, you are not able to recover this information. So for that, if you want to recover it, you would need to plug in some other mechanism and extend the RTP to recover that.
And maybe just a compliment to what Charlotte was saying. One idea that we did not experiment with, but which would be interesting to look at, is it possible to include some information about the error magnitude without having the update locking problem again? And one idea would be to track, for example, the norm of the error vector, but from the previous batches, and then to update or to adapt the values of gradients according to that error magnitude information. But this is something we did not really experiment with, but which is sure something we should look at.
Thanks. That's exactly like what I was thinking, because when you see them, I was kind of wondering what is actually the most important effect between the reduction of the effective learning rate or the class-dependent error magnitude. And I was kind of thinking there was a way like to make an experiment that would lead to this. So thank you for the pointers. I do have one more question, which is more of a general one. Do you have any plans to extend this work like to maybe other tasks, or to see this like if you can do with the forward unlocking, if you can get results on maybe some more complicated, like some more complex architectures and more advanced tasks than Cypher 10?
I think, yeah, sorry, go on.
Go on, Charlotte, go.
Yeah, I think the answer to that will be very simple. We'd be happy to collaborate on that.
Okay. That would be very interesting indeed.
Thanks for your questions.
Other questions? Charles has a raised hand.
Yeah, I have a very concrete question. What is the expected amount of savings you can have for the energy consumption of such a device that would implement GRTP with regards to what the actual devices can do?
So yeah, that would actually probably the detailed answers to your question would be found in this paper. So we have implemented. So it's the device, the network that we have implemented basically on here is a hybrid neuromorphic chip. So it's both spike-based, embeds convolutional layers and fully connected layers. And the fully connected layers are trained with the RTP. And we have compared, so it's a network basically whose format is similar to this one, smaller fully connected layers. A network is a bit smaller than this one. But we have compared the implementation without the RTP, so only for the forward pass, and with the RTP, and the overhead of embedding training is only 15% in power, so it's not an order of magnitude more. So that means basically training becomes really affordable with the RTP for edge devices. And in the paper, you can also look up the energy per classification and with and without training enabled for MNIST are provided in.
And maybe just to complement what Charlotte was saying, a more general way of thinking is that if you release the update locking problem, basically you do not need to buffer any for you have all the active gradients in your back, which is assumed both in terms of array on the chip, but also in terms of power.
A relier is necessary to handle the weight transposes.
Okay, thank you very much.
Thanks. Other questions? Okay, I don't see any raised hand or a question in the chat. The question I wanted to ask has been asked. So yeah, I think we can thank the speakers and close it here. I just want to remind you that we are gonna, like, this meetup is recorded, so we're going to put the video of the meetup on YouTube, on the LightOn YouTube channel, and we're also gonna write a short summary on our blog on Medium and post the slides there. And of course, you are welcome to contact the speakers if you have further inquiries. So thanks again, Charlotte and Martin. It's been really nice to hear this talk. And
thanks for the invitation.
Yeah, and we look forward to the collaborations then.
Yeah, sure. Super excited about that. Julian in particular. Thanks a lot. Bye-bye.
Thank you.
Thank you again.
Thanks a lot.